Projectile motion. Now, up until this point, we have been using phonemes to talk about motion in pretty much one direction, up and down, or left and right as it rolls along the ground. Projectile motion is kind of a combination of all of these ideas in the most complex type of motion that we're going to study. And basically, it has to do with what happens to things as they fly through the air. So our focus today is we're going to use phonemes in order to predict where a cannonball will land when it's fired from a high place. We have been using phonemes to figure out 5 different characteristics of motion: displacement in meters, velocity initial in meters per second, velocity final in meters per second, acceleration in meters per second squared, and then finally time, which is probably the most important. But it's always been in one direction, either the x-axis, which is left and right, or the y-axis, which is up and down. But when you throw a ball in the air, for example, a basketball, when you shoot it into the hoop, it travels in both the x and y-axis at the same time. In physics, anything that is thrown is known as a projectile, a body that is thrown through the air. And I have a little GIF here, and it shows the projectile moving through the air. And so it's pretty simple to think about balls as projectiles, but sticks can be projectiles, or rocks, or anything that moves through the air. The path that a projectile takes is called the trajectory. And this trajectory will be in the shape known as a parabola, which is this shape here, kind of this curve. One key element that we need to take into account is this idea of time. Now let's run a little bit of a thought experiment. If I were to have a gun that fired a bullet very quickly in that direction, but also have a bullet that I drop at exactly the same time, the question becomes which bullet hits the ground first. In physics, when you fire a bullet, it will take the same amount of time as a bullet dropped from the same height in order to hit the ground. You don't believe me? The Mythbusters proved it.
What you got there?
This is a good one. Picture 2 bullets, each exactly the same distance from the ground, each released at the exact same second, except one bullet is dropped to the ground, the other is fired from a gun. The classic physics thought experiment states that both bullets will hit the ground at the same time.
Based on what theory?
Based on the theory that the bullet that's fired from the gun has no wings on it, no lift. Thus, gravity has the same effect on it as it does on the drop bullet, and thus, they hit the ground simultaneously.
Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history.
All right, dude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet drop versus fired. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone. And the results are simply ripping.
Can't get much closer than that. Ugh. I can't wait to see the high speed.
Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves. And a victory for physics.
Let me put 39.6 milliseconds into some perspective for you. When you go to the movies and watch a projected celluloid film on the screen, you know that that film's made up of individual images, right? What you might not have known is that it takes 24 of those per second to make up the film that you're watching. So each one is on screen for exactly 1/24th of a second, but you don't notice that because it's faster than your eye can register. Well, that 1/24th of a second is actually longer than 39.6 milliseconds. That's how close those two bullets were.
So, the Mythbusters have proved that a bullet fired from a gun will hit the ground at the same time as a bullet dropped. And this is critically important at our deep dive into projectiles. This means if we can figure out the amount of time it takes an object to fall, we also know how long that object flies as a projectile moves through the air. And the upshot of this is that time fall equals the time to fly. If we accept that the amount of time it takes to fall is exactly the same as the amount of time it takes to fly, we can use this information to move between the x-axis and the y-axis to figure out all the other characteristics in either axis. Okay, a couple of things you get to bring to the party when you're solving a projectile problem. In the blue corner on the left side, if we just focus on the y-axis, the up and down axis alone, we've been studying, and there's a couple characteristics that we get to bring to the table. Number one, if things fall down, we say that the displacement is a negative number. And we do that because when people are asked which way is positive, almost everybody's going to point up. If that way is positive, that way needs to be negative. So as things fall down, they have a negative displacement. The second idea is kind of a joke that I make, the Wile E. Coyote effect. That if anything hangs in the air for a split second, we can call that velocity 0. And so, if something is dropped, its velocity initial is 0 meters per second. And number 3, if we are falling on Earth, we have established that the acceleration due to gravity on Earth is negative 9.8 meters per second squared. Which is cool, because as long as we're on Earth, we have an acceleration in this direction, as long as the thing is falling. In addition, we can add one more bit of information. In the x-axis, the red corner, when we talk about left and right, if you can actually ignore air resistance, then you can say that a projectile's acceleration in the x-axis is 0 meters per second squared, because air resistance is so small. Now, in order to explain this, I want you to think about when you throw a ball. So as long as the ball is in your hand, you get to apply a force. You get to push it, accelerate it, faster and faster and faster, until the split second that you open your hand and it begins to move away. Then your hand isn't pushing anymore on the ball. You are not causing the ball to speed up. As a ball flies through the air, the amount of air resistance involved in the ball pushing in this direction is incredibly small. So small that we could almost ignore it. Well, wait a minute. If my hand isn't accelerating the ball, And air resistance isn't slowing the ball down, it's not speeding up, it's not slowing down, and we get to say that acceleration is 0 meters per second.